Okay, nice with Dara, Croesio. Good evening and welcome everyone to this in the next in our series of inaugural lectures from new professorial staff. And I'm absolutely delighted to introduce Professor Yueng-Djern Lenn, who's Professor of Physical Oceanography from the School of Ocean Sciences. And I'm even more delighted to say that Young is one of 3 female professors who will be giving talks in this inaugural series. And I can see at least one in the audience. I won't spoil the surprise, but the other 2 will be giving their lectures soon. There's only, I'm sure John Turner won't mind me saying, there's only previously been one female professor in ocean sciences, Professor Hilary Kennedy. So this is the next generation coming through, and it's a much needed redress of equality and balance in the school, which is fantastic. It's also particularly resonant in that the university has just been awarded the Athena Swan Silver Award, which hopefully affirms that we've made significant initiatives and progress across the university in promoting gender equality and addressing challenges over the last decade from when we started on our Athena Swan journey. And this accolade is down to the contribution of very many individuals, including people like Young, who have been very committed to outreach, to communicating science to a wider audience, getting more people interested in STEM and attracting young people to the discipline. So perhaps just touch on some of the history in this field and the historical context in ocean sciences. Between 1872 and 1876, the British Challenger expedition circumnavigated the globe in a voyage that made the many discoveries which laid the foundations of modern-day oceanography. It's thought to be the first oceanographic scientific cruise, and the expedition was manned, and I used that advisedly, by 243 men because women weren't allowed on the cruise. And now here we have a leader of the cruise herself, so fantastic that we've got to this stage now. And a bit closer to home, the UK's first professional female marine scientist was a Bangor graduate. Rosa Lee, who lived between 1884 and 1976, was born in Conway and became the first woman to graduate in maths from Bangor University. She then became the first woman to be employed by the Marine Biological Association and also the first one to work as a fisheries scientist for the UK government. But unfortunately, she had to resign when she got married because that was the rules of the civil service at the time. But her seminal paper in Nature in 1920 on the growth of fish using the growth rings on their scales is still central to thinking, and the Rosalie phenomenon is still very much a part of the biology of that area. But anyway, to tonight's speaker, Young is a leading figure in a different aspect of ocean sciences and is a polar physical oceanographer. She works in a team in SOS that focuses on furthering our understanding of how the oceans work and how they interact with the other Earth systems. She's recently secured funding from the UK Natural Environment Research Council to lead a transatlantic team to better understand how freshwater from the melting Arctic ice will affect short-term weather patterns and improve the models which predict our global future climate, very pertinent to the current climate crisis. So her talk this evening is Warmth from Below, a Meeting of Ice and Ocean, and it'll give us an understanding of the myriad ways in which ocean processes across a variety of scales and in some unexpected ways release heat towards the ice and how these processes have changed over the last few decades. And she will also give us the implications of this in our changing climates. So, Professor Young, over to you.
Thank you. Thank you very much, Morag. Oh, gosh, amplification. Thank you for coming. And I should say, of course, as with all science talks, this is not work I've done by myself. You always work in a team, and you will get to see some of the pictures of my teammates shortly. But this talk, I should confess, I first wrote to give at the American Geophysical Union's general meeting at the end of 2022 as an invited lecture. And this was to the cryosphere section. So cryosphere is everything ice on planet Earth. Sea ice, glaciers, and all the ice that you can imagine that's sitting on the surface of planet Earth is the cryosphere. And so as cryosphere, science really includes a lot of glaciologists and a lot of snow scientists. I hope that this talk will be able to communicate the things that we have learned about the ocean and how the ocean interacts with sea ice in ways that are hopefully accessible to all of you. So the first thing I should say is that we do know that the Arctic is really responding to climate change much, much faster than the rest of the planet. And you can see that in this figure here. This is Arctic temperatures, and you can see they're going up much quicker than the average global temperature rise as a result of climate change. At the same time, What we can tell from ice volume in the Arctic from previous measurements and models is that there has been a lot of variability through the 20th century, say from beginning of the 1900s. But when we got to 1990, this was the start really of a precipitous decline in sea ice volume and extent, which coincided, this is 1990, you probably can't see, with this Arctic amplification response to climate change. So sea ice really has a part to play in this Arctic response. That is because ice everywhere is white, and this white ice is particularly excellent at reflecting solar radiation back out to space. So the ice on planet Earth is a really important part of our energy budget. It keeps us cooler than we would otherwise be if our Earth and ocean systems absorbed all that solar radiation. But what happens when you lose the ice? It turns out that the darker land and sea below it are much less efficient at reflecting that solar radiation back out to space. So yes, the land and sea absorb that solar radiation instead of pushing it back out to space, amplifying warming in the Arctic relative to other regions that don't have ice in the first place. So this is what we call the ice albedo effect, and it's a really important component of our Earth's energy budget. And so you see we are really interested in all the processes that can contribute to melting any of the ice, both in the ocean, which is the sea ice, or the glaciers. Is there a problem with my mic?
I think so, yeah, possibly.
I mean, it's too loud, isn't it? Okay, shall I whisper? So, sea ice is really important. So you want to swap it?
Swap it, or we can.
Okay, we just use this. Okay, we just use that. See, that's how loud I think I should be in all my daily life, of course, particularly when talking to children. So, okay, so sea ice then also plays into the Earth's climate system in other really important ways. One of which is that when sea ice forms, so sea ice specifically is frozen seawater. When it forms, what happens is that the part that freezes is the freshwater content of your salty seawater. This leaves behind the salt that was there in the first place and concentrates the salt into really salty brines. These salty brines are denser and heavier than the seawater it was formed from. And so this process known as brine rejection means these salty brines drop down away from the sea surface, and they contribute to the formation of cold, high salinity water. And cold, high salinity waters then play into ocean overturning. So this transformation of seawater in what was at the surface formerly by losing heat to the atmosphere and forming sea ice, then transforms into this cold, salty water, and that from the Arctic contributes to dense overflows, which are part of the global overturning circulation. So you're just seeing here a figure of the Atlantic meridional overturning circulation component of what is really a big ocean conveyor belt of heat. In this particular system, you have warm water, which has been warmed by the sun in the tropics, and it flows north or towards the polar regions. The same happens in the Southern Ocean. Flows towards the polar regions, where it gets to places where it can lose lots of heat to the atmosphere, so the warm water becomes dense cold water. And this sea ice formation process contributes to the dense water formed in the subpolar North Atlantic and the Arctic. And that flows back to the lower latitudes at depth below this warm water at the surface. This is a gigantic redistribution of heat on the planet that is done for us by the oceans and atmosphere system together. And without the overturning circulation, we would not enjoy the relatively warm weather that we enjoy here in the UK. It is really a fundamental part of our global climate system. And sea ice is a part of this system. Now, the other way in which you probably are more concerned about the sea ice is that we've been able to show that say in the Barents and Kara Shelf Seas, which are here, north of Norway, east of Greenland, these kind of Arctic continental shelf seas, the loss or the extent of sea ice in these regions has been shown to be strongly linked to extreme weather in the northern hemisphere. And in this particular study, what they found was that there was a strong correlation between low sea ice in the Barents and Kara Seas and a warming of the Tibetan Plateau. And the way in which they think this is working is that when the ice is gone, the ocean is in direct contact with the atmosphere, meaning that it can lose its heat much more quickly to the atmosphere than it would if the ice was in the way. So what we are expecting is that with the loss of sea ice, you're getting enhanced ocean-to-atmosphere heat fluxes. Remember, the ocean is generally warmer than the atmosphere at these latitudes because it's still wet. And this can amplify waves in the atmosphere. So waves in the jet stream, waves in atmospheric currents that then results in the drawing up of southwesterly winds across the Tibetan Plateau. Therefore, these winds that come northwards are coming from lower latitude, warmer places that warms the Tibetan Plateau as a result of a process in which heat from the ocean in the Kara and Barents Seas destabilizes the atmosphere in ways that can affect you and I much further afield from the Arctic. So we're really interested then in processes involving sea ice and how much there is, and so on and so forth. But to those of us who are curious scientists who want to go to the Arctic and make measurements, sea ice has also been tremendously important as a platform for science. So here is Mr. Nansen, and he, in the late 1800s, set off in his ship, the Fram. And of course, those were the days of, these butch explorers who really wanted to do things like get to the pole first. And so he had this clever idea, together with his colleagues, of taking their ship up into the Arctic and letting it get frozen into the sea ice sheet north of Siberia. Because from Siberia across the North Pole towards North America, there is a prevailing drift of sea ice. So he was thinking, we'll freeze the ship in, and the drift, or what is called the transpolar drift, will carry us across the poles. And then we will wave our flags as we go by, and then we will come back to tea and biscuits. Well, I don't know, the Norwegian equivalent of tea and biscuits on the other side. It turned out, as with most expeditions, not to be successful in that way, but he still made it to the furthest north. And there's an excellent book that you can read, The Farthest North, about his amazing expedition where they went so far, the ship didn't seem to be going farther north, so he and two buddies got out and said, we'll ski there. Now, this is like almost 10 degrees of latitude to go before they can get to the North Pole, but they're going to do it, and then they get out and they go for a bit, and they're like, no, it's too far. And so then they ski back to, not the ship, because the ship was moved on by then. Eventually, they ski back to some islands, and it takes a whole nother year for the ship to come out the ice. So that's their exploration, fascinating. But also, Mr. Nansen, I suppose this is the case of the explorers who also wanted to do, now we have greenwashing. This is science washing. So he also did some science because he had this ship up in the Arctic. He was like, okay, I'm going to take scientific measurements. And I want to measure the ocean. So he and his cohort invented several instruments to measure ocean temperature below the surface, as it were. So it wasn't a case of just putting a thermometer into the surface ocean. They lowered a bunch of instruments and they measured all sorts of things, which gave him the most amazing discovery. So in most of the global ocean at lower latitudes, because the sun is shining on the ocean, it's warming that surface layer, causing evaporation. So you tend to have warmer, salty water at the surface and colder, fresher water below. But what Nansen found is that the Arctic was upside down. It was upside down in that the cold, fresh water was at the surface, and this warmer, salty water was at depth. So it's what he called the upside-down ocean, and he was able to make this discovery. The instruments he invented, which are predecessors of the instruments that we use today. So kind of expanding oceanography for us in an important way. More recently, the ice also has been used as a platform for international, large-scale experiments to make measurements in the Arctic. The first one in the late 90s was the Shiba experiment, and its track was up here in the kind of western sector of the Arctic. So this here is North America, Canada in particular, and Siberia is here on this side, and their track was COMSAR, and they made really big, important breakthroughs in Arctic cloud dynamics, looking at the way the oceans, the ice, and the atmosphere exchanged heat and the radiative balance of the planet. More recently, in 2015, the Norwegians again, went out in this expedition they called an ice experiment, the Norwegian Young Sea Ice Cruise. By this time, 2015, we already know that we've lost a lot of sea ice, and the ice that is present is young in the sense that it tends to be not so much really dominated by multi-year sea ice that has lasted from one season through the summer through many years. Generally, we're getting more first-year ice these days, or at most second-year ice. So they went and froze their ship out, and they did, as you can see, several different drifts over the course of the NX experiment to look at the response of younger, thinner pack ice in ocean to open ocean storms, and to look at productivity underneath or amongst the ice. And then, of course, most recent of all, 2019-2020, was a huge international expedition in which the Germans froze the Polish stern into the ice. They were going to attempt to recreate Nansen's voyage, but with the Polish stern, you see they went out over towards Siberia. They froze themselves into the ice, and then the ice did what it did, of course, and then COVID came as well. So, it was supposed to be 2-month-long legs that people were out for. Then giant icebreakers would break their way to them, refreshing the crew and bringing supplies. And in the end, one of the teams did actually spend 4 months on the ice before they could be resupplied, before anyone could figure out how to do it during COVID, as it were. So effectively, this experiment was any type of science that you can imagine. There were planes, far field, doing atmospheric studies. There was all kinds of instruments that they drilled through the ice and lowered into the sea. Lots and lots of observations to really document the Arctic Ocean response across the middle of the Arctic Ocean, really to climate change, from the top of the atmosphere to the sea floor. And so what I should say is the rest of this talk, I'm going to tell you about what we found in my project, Peanuts, that contributed to this Mosaic expedition. So I'm going to put my Peanuts hat on, and I will speak to you as the lead scientist for this project, in which we pose the question, is primary productivity in the Arctic driven by escalating Arctic nutrient fluxes? So we were motivated to pose this question because observations from satellites of chlorophyll in the Arctic Ocean, where we have seen open water, have shown that the phytoplankton in the Arctic have been really productive in a way that exceeds what you would expect, because they photosynthesize, so they need light, and they get more light as the ice goes away. But they have been more productive than just the extra light availability from the declining sea ice would suggest. So there is something missing in how they are able to continue to be so productive. And so we thought it might be because there is a big supply of nutrients to the Arctic surface waters as a result of this declining sea ice. So we went out to make measurements, to look at how ocean mixing is driving nitrate fluxes into the surface ocean. And I should also say, remember that warm, salty layer below the surface? That warmth can also be mixed up at the same time as nutrients into the surface layer. So Arctic-ocean mixing is a really key question of how much the ocean is going to be contributing to sea ice loss. And so these are the objectives that we had in that project, and these are all the people, but it's much more fun to look at their faces, isn't it? Yes. So here they are. Some of them are in the audience right now. I can see them. I can spot them. Okay. And what I would like to say is that in this picture of the Arctic Ocean, over here, you can see red arrows and yellow arrows, and they represent inflows from the lower latitudes to the Arctic Ocean. The red arrows are the Atlantic water inflow from the North Atlantic, coming past Svalbard, in between Svalbard and Greenland, and it circulates around the margins of the Arctic in other ways as well. And then you have an inflow here from the Pacific, and you have an inflow for the Pacific, and both these water masses are warmer than local Arctic water masses, and they do carry nutrients from the lower latitudes into the Arctic. So they are sources of nutrients for the Arctic. And you're like, but why does it need nutrients? Doesn't it have nutrients already? Well, yes, it does. However, let's take a look at a cross-section of the Arctic Ocean. And the cross-section is going to go from Fram Strait over here on the eastern side of the Arctic over to the Bering Strait on the western side of the Arctic. And just to confuse you, I'm going to put the eastern side on the right-hand side and the western side on the left-hand side. But you'll be guided by, you'll be guided by the colors, because the red, as before, is Atlantic water. The orange, as before, is your Pacific water. Okay, so you've got Pacific water. So this is the Pacific side, here's the Atlantic side. And what you can see if you look at the Arctic Ocean is that there are lots of different, what we call layers in the ocean. So you have light water sitting on top of denser water always in the oceans, and these layers are made of water from different origins. Okay, so you have your kind of surface, cold, fresh mixed layer at the top. And where does the phytoplankton live? The phytoplankton, in order to photosynthesize, has to be in the sunlit euphotic zone, the part of the ocean that gets light from the sun. So if it's up here in the sunlit euphotic zone, what happens is that spring comes, the ice goes away a little bit. This is too hot, so I'm going to take it off. Okay, so the spring comes, ice goes away a little bit, and so you start getting light penetrating into the ocean. Phytoplankton go, yippee! We're going to eat up all the nutrients that are here and bloom, bloom, bloom. So that's what they do, and they quickly, very quickly exhaust the nutrient supply that has accumulated over the winter. And so what you need then to sustain a bloom past the spring is extra supply of nutrients, because you still have the light, but you don't have extra supplies of nutrients unless you have some process that can mix your deep nutrients upwards into your euphotic zone. All right? And so here are a zoo of different processes, and we will briefly, in a tour format, so as to not be too physicsy, discuss the importance of these different things. So when we went out, when Bangor initially went out to join an Arctic cruise in 2007, 2008, we made all these measurements of ocean temperature from the surface down to about 1,200 meters. And what you can see is that there was a warm surface layer. This was the summer, so it was actually really warm that year. And then there's a cold, because temperatures on the x-axis, so cold is towards the left, warm is towards the right. So there's a cold surface layer, and then that's this deep kind of warm layer, and that, of course, is that Atlantic water that we measured down at 300, 400 meters approximately. And right in this zone here, as you transition from the cold to the warm Atlantic water, we saw all these kind of staircase structures in the temperature. Salinity is on the right, and you can see as you go down, you increase in temperature. As you go down through that layer, increase in salinity, and you have steps in both temperature and salinity. This is a sign of a process known as double diffusion. And it's called double diffusion because it really depends on the molecular rates of diffusion of heat and salt. Heat diffuses much quicker And the way I always describe it to my students is that if you think about a disco, heat is energy, really. So if somebody starts wiggling in the corner, it's quite easy to get lots of people wiggling, and the wiggling can transfer across the room much more quickly than the person actually getting across the dance floor. So the person actually getting across the dance floor is the salt. So that's slower than the heat. So if you do that, if you transfer heat from a warm salty layer up, then this makes this water, as it gains heat, lighter than the cold water above it, and it convects away, while the salt remains in this layer below. So effectively, this reinforces interfaces, which gets you this development of staircase structures. This is a slow process because molecular diffusion is a slow process. And this, you can see that from the fluxes we measured through the staircases, they were a whole 10 times too small to explain the heat differences that we saw between these profiles as you went along this boundary current. So our observations then reinforced the notion of the Arctic as a really quiet place where we didn't have a lot of vigorous mixing, because we were making measurements here on the continental slope, which is generally thought of as a more active mixing place. And you can see that actually back then, so it turns out that 2007 was the first really record low sea ice extent minima that really made the headlines. And it was so much lower than the kind of trend of declining sea ice before that it invoked lots of study, of course. And what we found is really that ice albedo effect was at play. So as the sea ice was lost, more warm ocean was exposed. And Don Perovich and colleagues found that the ocean absorbed this much extra solar radiation than it did in other years before that. And this extra radiation was more than enough to account for the melting of the sea ice that we saw in this sector. So in other words, in the late 2000s, what we really saw is the ice albedo effect, and local solar radiation was kind of more important for driving sea ice loss at that point. Has the story changed? Well, we shall see. Okay, so we've talked about the double diffusion process. It's not very important for bringing heat to the surface ocean. How about wind mixing? Now, this seems an obvious candidate because as the ice goes away, the ocean is in direct contact with the atmosphere, which means the winds can more easily transfer their energy and drive big currents to the ocean. So if you can get the surface ocean moving really quickly, then what you get is a change in currents across the base of that surface mix layer, which maybe can cause wave breaking and drive mixing. And what we found when we went out in 2012, which is also another record minimum sea ice year, is that in this sector of the Western Arctic, in the Beaufort Gyre, this is an area known as the Beaufort Gyre, what was effectively the Great Arctic Cyclone of 2012 did indeed occur when the ice was absent, and it did drive big currents in the ocean. And there was a big difference between the top currents and the subsurface currents, but the mixing measurements that we made showed that these weren't really associated with particular wind energy inputs, or that it was able to drive very much mixing, because if you have a very stably stratified ocean, in other words, very, very light water, lots of it on top of much heavier water, you have to put more energy into this system to mix it than if you had a system that is weakly stratified, where the difference in density between your layers is much smaller. And in the Arctic Ocean, we found that mixing was suppressed by basin stratification. So again, that reinforces the story that, it's going to be solar radiation from the sun and the albedo effect, which is more important. So maybe Atlantic and Pacific heat aren't so important. Well, then we get to the question about tidal mixing. What happens there? It turns out that, so the tides you and I see around Bangor, they're huge relative to most of the rest of the world. Right? Tidal ranges in the deep, deep ocean tends to be very, very small. You can barely see the tidal wave as it goes through. Sea surface height doesn't change. You don't get kind of tidal maxima in the same way. But on the continental slopes, and also on the continental shelves, as it gets shallower, all that tidal energy that was formerly in, say, 5 kilometers of water is now compressed into much, much shallower areas. And you can get the breaking of, we think we can get a generation of things that allow for mixing from the tidal energy input to the ocean around the margins. And this is a paper that we published in 2015, in which we looked at measurements all around the margins of the oceans, and we found that there was some kind of correlation, definitely, between the energy coming out of the tide and going into the ocean and the mixing that we were seeing. So we did think that mixing of Atlantic water just on the continental slopes could be important. Now, when you think about mixing from the tides, generally for a layered ocean, you think about a tide going back and forth, perhaps over either a hill, which is this subsurface seamount, or just, if you just think about one side of it, that's a continental slope, all right, where you just get like the maxima going down to the deep. But effectively, if this pattern is going back and forth, the tide is pushing these layers back and forth across the seamount, you can see that the layers could be drawn down on one side of the seamount, in the lee of the seamount, and vice versa when the tide reverses on the other side. This then develops these kind of fluctuations in the interface between those layers. This is what we call internal waves. And in most of the world oceans, say about below 75 degrees north, the physics allows these waves to propagate away from the generation point. So they take their energy away. These fluctuations just keep going along these interfaces between layers and take the energy away, and maybe somewhere else these internal waves will break. And we don't know exactly when and where that happens. However, the special conditions of the Arctic, and this has to do with the Earth's rotation, which I think I won't get into here, but it just means that at these latitudes, the kind of twice-a-day tide, which is the biggest component of the tide around here, that can give energy into this internal wave system, generates internal waves at that frequency, so it's a twice-a-day internal wave signal, that cannot propagate, cannot go away. It cannot go away because of kind of physical limits to do with the rotation of the Earth at these latitudes. And if it cannot go away, that energy, instead of forming what we call linear propagating internal waves, can go into non-linear internal lee waves. And it's kind of trapped on one phase of the tide, and as the tide releases it, these things can break. So you can imagine if you get wave breaking over here, at these kind of internal interfaces, you can get a mixing of quantities from this layer and this layer if this wave breaks, right? And so we did find some circumstantial evidence for this process that was modeled. And here, this is north of Svalbard. These are some observations by colleagues, Ilke Fur and team. And what they found was that, yes, in this particular case, the once-a-day tide, it turns out, pushes currents offshore. So it pushes the currents offshore, and then it pushes down these layers, interfaces. So it pushes down the surface of constant density, which lies between the layers, and you get this depression here. And it coincides with a hydraulic condition that you compute from the velocities and viscosity and gravity and so forth. And it corresponds with the Fruit number being raised to above 1, which is the condition for which we think nonlinear waves can form. So these nonlinear waves then form, and do they mix? Well, the mixing measurements, which are these colors here, number 4, show that there is indeed a high dissipation, which amounts to mixing. So that's kind of interesting, because what we've shown now is that we have a process by which tides can drive mixing in a way that is unusual for the rest of the global ocean. in the Arctic. But this generation of nonlinear internal lee waves doesn't have to be from just the tides. All you really need is a process that can drive currents offshore. And it turns out that we made some other observations here, north of Siberia, where we found large currents being pushed offshore out to sea. And you also had these, and this figure here is the depth of layers of constant density or interfaces between those layers. And those layers at the same time are being pushed down. And when we made some mixing measurements alongside of those, you can see in the red, the mixing associated with just such an event was much, much bigger than these background values in the black. What does this mean? Well, we think this is a storm-driven process, but it's not a storm-driven process in the classic way, where the storms come, put energy in here, and then you get stuff happening. We think this is a storm-driven process in a much more unusual way. So Seth Danielson proposed that when you get a storm, now you and I know that storms are associated with low pressures. So what does a low pressure do? It drives a storm surge by sucking up the sea level. So you get this hump in sea level under a storm. And so that makes effectively a disturbance in sea level on the continental slope for a storm that forms on the continental slope. And this disturbance can propagate away from the storm generation point. So days later, you can get big currents being pushed offshore, far away from the storm generation point. So this is really an unusual thing that we didn't think about or know of before. We thought that this was the process that might be driving our mixing that we saw. So what is the impact then on nitrate fluxes? Well, here are background fluxes, and here is the value that we found from that one big, huge event. It represents a 1,600% increase on nitrate fluxes, and there was associated locally enhanced primary production that fed off these extra nutrients that were suddenly available to them. And then at the same time, I should say that, of course, we can also be fluxing heat from that deep Atlantic water layer up to the surface in the same way in a huge kind of episodic event as a result of these storms. And are these storms becoming more prevalent with the absence of sea ice? Well, Kiki then went to have who was the author of these papers, then went to have a look. And here, these lines are sea ice concentration, and the stars are when she identified what we think are storm mixing events. And you can see that these storm mixing events predominantly do happen in ice-free ice or low ice or ice-free conditions relative to when you have 100% ice. Still happens then as well, but more with more open water. So this suggests that actually, as we get more open water, ocean mixing of heat and nutrient fluxes to the surface is becoming more important, but in a way in which we hadn't predicted before. And it continues to not be represented in global models. Pardon me. I need to stop talking all this. Soon. You'll be glad. At the same time, I guess I should say that all this is happening. We've also had a warming of this Atlantic water inflow. So this is a warming of the Atlantic water inflow observed at the Barents Sea opening in this location here. It's gone up pardon me. It's gone up in time, and at the same time as it's gone up, it's also held back the sea ice to farther northerly latitudes. The sea ice comes and goes with winter, retreats in summer, comes in winter, retreats in summer. And as time has gone on, once we got past about 2005 in the Barents Sea, the sea ice really stopped coming even in the winter past the polar front up here. At the same time as which that happened, in this location here, we've also noticed the depth of that warm, salty Atlantic water layer getting closer and closer to the surface, suggesting indeed the heat fluxes from the Atlantic water are having more and more of an impact on sea ice and also the nutriscape. I guess the last thing I want to say about that is that, so here are the background fluxes, and what we think has been happening over the last, since the early 2000s. But now, as the Atlantic water is pushing west, we think that this might be happening. The Atlantic water pushes west, these fluxes are going to increase, so at any one latitude, you're going to get an increase in nitrate fluxes. So Atlantification will definitely, we believe, enhance nutrient fluxes, particularly along the pathway of the Atlantic water. And in some work that was done by one of my MSc students who's sitting in the audience today, it's actually been really hard to get evidence to show that mixing has increased in any way in the Arctic. But this was a nice little bit of work that she did in which she compared the layering of the Arctic Ocean, and that's what this equation is. It's the only one, don't worry, there won't be any more. This equation really tells us how much energy you need to totally mix a water column. And she compared kind of late fall to summer conditions, so June minus October, and what we see is this increase over time. And this really is the first sort of evidence that has shown us there are trends indeed in Arctic mixing. And this was happening on the Laptev Sea. Okay, so we know mixing is becoming more important and in ways that we hadn't expected before we went out to make all these observations. And we've talked about how those things, both tidal mixing and wind driven mixing, are helping to internal wave breaking to drive heat fluxes. And you're like, okay, well, let's not be one side of the planet east. Let's think about that Pacific water as well. What's happening there? Well, here is where we'll talk a little bit about eddy stirring and what eddies can do. And effectively, we went out and joined some colleagues who were making observations in the Beaufort Gyre, and they were fortuitously able to observe this warm filament of Pacific water, which would normally be flowing along the coastline, actually extend out into the middle of the Beaufort Gyre. And these lines here show you where that Pacific water is on this is a temperature salinity graph, but just to say, just look between these lines here. The colors are, in this case, nitrate. This Pacific water has actually traversed the shelf here over the last summer, and it's had lots of its nutrients stripped out, but below, there's plenty of nutrients that are getting drawn up into that Pacific water. At the same time at which you see quite a lot of chlorophyll being vectored out into the Beaufort Gyre alongside that Pacific water. So that can respond then to those nutrient fluxes. And it's this action of this filament that is drawing the nutrient fluxes up. So now, this is the best bit of the talk because you get the nice soothing video with cool music that will hopefully not put you to sleep, but we shall see how that goes. And so this is the video that my colleagues at Scripps made of the science that they did there. And so that you see what I mean about this new agey music. I shall leave you to watch it. And this was Ben Barton, my student who went and joined Jen, who was the leader of that cruise. So this is all footage taken from their cruise. Very fresh layout surface. Looks like an alien, doesn't it? This is how they got this into the press, by calling them heat bombs. Okay, so we could watch to the end of that, but I don't think we will because it goes on for a bit and it's all the acknowledgements. But suffice to say, this work was supported not just by the UK's Natural Environment Research Council, but by the Office of Naval Research in the US as well. Okay, how do I go to the next slide? There we go. And so what impact does this have on primary productivity? You know, because you're thinking, she promised me primary productivity. Well, this is another MSc project from a student who has now finished her PhD in St. Andrews. And she ran a model to look at where you get spikes in nitrate fluxes. So this is the ocean mixing model in red. And this is giving you spikes on nitrate fluxes at this location here in the Beaufort Sea. And in green, you have the response of an ecosystem model that looked at total new gross primary production, or the response of the phytoplankton, basically. And what you can see is at the start of the melt season, when the light comes back, they don't need nutrient fluxes because all the nitrates that have been there all accumulating over the winter, and they bloom like this. But subsequently, they don't bloom unless there's a new influx of nitrate to the surface ocean. And then if you look further on in time, as the freeze begins and the light goes away, it doesn't matter how many nitrates you stick into the surface ocean, they're not going to bloom anymore because there's no more sunlight. No more sunlight. Okay, but then you can see here as nitrates will continue being fluxed into the surface, and that's how the surface layer accumulates nitrates throughout the winter. Okay, so midsummer fluxes are important for sustaining blooms. This is the end of the science bit. Hurrah! Okay, so how much does sea ice experience of the warmth from below? The Arctic Ocean, we know, is warming and the ice is melting. And it is in part due to warming of the Atlantic water and Pacific water. And for the Eastern Arctic, it's a process known as Atlantification. Now, winds and tides are driving mixing in unusual ways, unusual for lower latitudes. And these processes are still not represented in the climate models that we use to predict our future climate. And you can see a result of not representing such processes here because in 2022, there was a huge-ass storm in the Barents Sea, a mega storm that they hadn't seen the lights of before. And what they found is that the sea ice, here are the observations in black and all the models in the other colors, they lost a lot of sea ice to the north of the Barents Sea on that shelf break edge that they didn't predict in the models. And they didn't understand. So this, to me, circumstantially suggests that this is an example of that remote wind mixing mechanism that we talked about. And what we know is that mixing will most likely increase as the ice recedes for multiple reasons. And the result of this is we're going to get more nutrients and more heat into that surface ocean. And it's now has been shown to become as important as local radiative forcing. So the consequences for Arctic primary productivity are then that it's going to be enhanced by accelerated Arctic mixing. So the answer to the original question is yes, primary productivity is enhanced by escalating Arctic nutrient fluxes. And No Science Talk is complete without acknowledgements, not just of the whole Peanuts team, other investigators in Germany and the UK, as well as our collaborators, international collaborators from the US, Norway, more US, more Norway, more UK. And then also, we did a bunch of other things. We wrote lots of papers. We had, and we also produced an all-program STEM product, which is the Changing Arctic Ocean Challenge Cards. This is a Top Trump style game that featured the science of the Changing Arctic Ocean program, of which Peanuts was a part. So it's like a 16 million UK, Germany program of science. It has all interdisciplinary science in it. You can have yourself a pack if you're quick enough. They're on the table outside. But I can't end here because I need to be able to say that, you know what?
You know how it takes a village to grow a child? Well, it really takes a village to, I guess, grow a professor. Because, you know, I would not be where I am today without the encouragement and the mentorship of many, many people. And I have to say thank you to my department, particularly many of my colleagues in ocean sciences. And if your picture is not there, it's because I couldn't find a funny one of you. So, not because I'm not grateful, but effectively, many of my colleagues at Bangor and also beyond Bangor, thank you so much for your encouragement and your just being great colleagues in general. I mean, ocean sciences is a really collaborative. We have great teamwork, and I really appreciated that, particularly in those hard COVID years when several of us were out of action for one reason or another, and that included me. So thank you so much for all that. And I should also say that I can't leave this talk without taking the opportunity to embarrass my children. And so therefore, of course, I would like to thank them for their support as well. This was taken during COVID era. Okay, thank you very much.
Thank you, Young, for an excellent talk. I'm sure there's some questions for Young.
It's all crystal clear.
Absolutely. Ice clear. If you could wait for the microphone so that it appears on the recording, that would be helpful. Thank you.
Oh, I can't walk past this. Oh, there's a tape on the floor. I'm not allowed to walk past it because I'm not on the video then.
What I would like just to ask is, if the Atlantic overturning ceases, how will that actually... what will happen in terms of your predictions and things then? Because it may well cause it to get colder rather than hotter for some parts of the ocean.
That's an interesting question. So are you referring to that film, The Day After Tomorrow, where, you know, they had like a giant freeze, these mega storms? It was very, very dramatic. I have to tell you that several friends and I was doing my PhD at the time, we went and saw that in the cinema, and all the ice scientists were laughing when he jumped across this crevasse. They're like, oh yeah, that would be me. But no, okay, I digress. So if the Atlantic overturning circulation was to stop, then yes, we would see drastic climate change. And there's people who think that we are close to a tipping point. But I think a lot of the answer of what is going to happen really comes to a better understanding of how the ocean and atmosphere interact. So, you know, are we going to get a change in the storm paths because AMOC closes down? Or have we already seen that with what we believe has been a slow weakening of this Atlantic meridional overturning circulation? There are people in the room who have better answers than me, but I'm not sure if they're awake. But one of my projects, which we are just going to get online now, is going to look at the impact of freshwater. And freshwater is a really big key to this. This is how we think it might stop. If we get enough freshwater into the surface Atlantic Ocean, this is going to be a barrier between what's normally that warm kind of Atlantic water coming from the subtropics. And for that water to not be able to lose heat to the atmosphere, it could turn off its overturning. At the same time, we know that, you know, we're going to keep going around the sun, and we're going to keep rotating as well. So as a result of those things, there's always going to be sea ice formed in the Arctic in winter. And so that component of the deep water formation is not going to go away, but it could change. So I don't know. What do you think, Sheldon? Yeah, so if you want to give Sheldon the microphone, he'll tell you a little bit more about AMOC. See, I brought the people with the answers.
This is your show. The AMOC's not going to stop.
No, we don't think so. That's the short answer. So every time you see huge headlines, because that's how people get their science in the press, by trying to say something really provocative, don't be concerned so much about these tipping points, because the Gulf Stream's always going to keep flowing because it has to, because of the way the winds work, and that's not just a part of the fact that it contributes to AMOC. So, any other questions?
I have a question, Young, what people are thinking. These are obviously circulation patterns on a huge scale. What about the relatively short-term changes due to something like El Nino? What does that impact does that have on ice?
So El Nino is a phenomenon, as you all know, that happens in the tropical Pacific. So it's really quite far away from the Arctic. However, you know that process where it talks about the loss of sea ice in the Barents Sea, which allows heat fluxes from the ocean to the atmosphere that can destabilize the atmosphere. Similar things can happen during an El Nino. And so the tropical Pacific can impact the atmosphere in a way that allows disturbances to travel long distances to other parts of the globe. So we can't say for certain exactly what is going to happen from one El Nino to another, but and these continue to be areas of intense research to try and pin down the what are called teleconnections over these long distances between El Nino and weather patterns in farther afield. Yeah.
Thanks. The primary production you've been analysing is also important in the carbon cycle. How have you assessed what impact that has on the carbon in the oceans?
Well, that wasn't part of my project. That was not a question that we tried to answer within the Peanuts project. But as you can imagine, it's a question of great interest to many people, and it remains an active research topic. So the deal with how much carbon you can draw out of the atmosphere and get the oceans to hold on to for long periods of time really has to do with not just whether you can get the phytoplankton to bloom, but are they the right phytoplankton that are untasty? So this is what they found in the Antarctic, in the Polynia. These phytoplankton were untasty. Nobody wanted to eat them. So when they died, they just fell to the sea floor. So that's a really big carbon flux. You see, and there's phaeocystis. And you see, I'm just impressing my biology colleagues that I know some biology words now. But effectively, it really depends on which phytoplankton respond and which species are around to eat them and whether or not that gets recycled in the surface or whether it gets exported to the deep. So the connection between the surface ocean and the deep ocean remains. Physics is much easier than biology. It remains really complicated, and and it's kind of a hot topic, as it were. So I can't give you the answer to that. So until we know more.
Okay, well, we're right on time. There'll be an opportunity to chat to Young over refreshments in the foyer, and if you're quick, you can get a pack of cards. But I think we just thank Young once again for a fascinating talk.
Really good. Really good.